In the last video, I tried to cram as much information as possible into a 10-minute video. I also went into a highly detailed analysis of all the math in Frank's paper. Now, most people don't like math or understand it, so most people really didn't get a lot out of the video. So I've invited Frank to a one-on-one discussion of this seminal paper. He and I are going to try to break this down as simple as possible for everyone out there. Frank, welcome to YouTube. Thanks for coming on the show.
Thanks for having me on your show, Jeremy.
So Frank, why don't we start with some history of modern physics for everyone out there. Let's start with Newton and talk about Einstein and where physics is at today and what the problems are.
It's interesting to put things in a historical perspective. In ancient times, the philosophers of that period, such as Aristotle, tried to understand the workings of nature through a process of introspection. They closed their eyes and they looked inward, and they tried to understand it from the inward psyche of the human mind. And that was the prevailing philosophy for 1,000 years or so, until Newton arrived on the scene. Newton looked outward. He looked at experiments. He looked at the physical reality of the universe. And what Newton did was he applied mathematics to physical laws, and he showed that nature obeyed the laws of mathematics. Newton's was a clockwork universe. It's like if you had billiards on the table. You hit the cue ball and you knew the exact position and momentum of every ball. You could exactly compute the outcome. At the end of the 19th century, Newton's laws explained just about everything. There were just a few small points to pick up.
So what happened at the end of the 19th century to change this?
At the end of the 19th century, Newton's laws of motion reigned supreme. It was felt that everything that there was to explain, everything about the universe, could be explained through the application of Newton's laws. And at the Solvay conference in 1911, cracks began to appear in Newton's formulations. Newton's formulations could not explain the emission of a black body. What that means is if you put a poker into a fire, it'll first turn red hot, and then if you heat it more, it'll turn white hot, and if you get it very hot, it'll turn blue hot. Well, Newton's laws of motion could not explain the color of these emissions. Maxwell Planck came up with a radical explanation that explained the emissions of a black body. And his explanation revolved around the idea that nature, on the very most fundamental level, was constructed around tiny particles called quanta. And that light that was emitted from this black body emerged as quantums or particles of light. And this formulation exactly explained the emission of the black body. Niels Bohr applied Planck's constant to the atomic structure, and he found that each electron orbits the nucleus, and the amount of angular momentum contained in this orbit is described by Planck's constant. These states are called stationary quantum states. And so Planck's constant then described atomic structure. A global philosophy emerged from this understanding, and it said that Newton's classical laws did not reign supreme. They were a subset of the true laws of nature, and these true laws of nature were quantum.
Now this model, despite having the problems you pointed out, has served us right for the past 100 years. Cell phones, radios, computers, all our communications technologies are based on quantum mechanics. Why change the theory now?
The problem with quantum physics, and I can't say this loudly enough, is that Planck's constant is empirical. It was extracted from the observable results of experiments. It cannot be produced by fundamental analysis. What does it mean? Where does it come from? Nobody knows. And the use of Planck's constant produced an enormous number of mind-boggling inconsistencies that can't be explained. One of them is the problem of amplitude and frequency. For instance, if you're standing in the ocean and a wave hits you, the amount of energy that wave hits you with is proportional to its amplitude. The bigger the wave, the harder the impact. But if you're laying in the sun and you get hit with infrared heat rays, it doesn't really burn your skin. But ultraviolet rays do, because they have more energy. And so the energy of a quantum system is proportional to its frequency. So there lies the inconsistency. Amplitude explains the energy of a classical system. Frequency explains the energy of a quantum system. Now, in order to try to get some meaning out of this, the principle of quantum correspondence was invented. It says that the amplitude in a classical system corresponds to the frequency of a quantum system. So if you sort of get enough brainwashing and squint, you'll see that there's something to this. There's a problem with this. There's a basic problem with quantum physics. It cannot be explained. It doesn't make a lot of sense in all instances. And Einstein realized that. In 1935, Einstein, Polesky, and Rosen wrote a paper. It's called the now famous EPR paper. It says, is quantum mechanics really complete? Could all of these inconsistencies be explained? Is there a hidden variable or something that we don't understand, that if we really knew what it was, this stuff would gel and everything would flow together and it would be a consistent pattern that would be very understandable?
How did you get into this field of research? Where did you start? And why are superconductors important in all of this?
I became interested in this whole thing because I wanted to control gravity. And I was looking for a condition that dramatically alters the range and strength of the natural force fields. And I looked into superconductivity, and I found some amazing things. For instance, the magnetic field is completely expelled. It's called the Meissner effect. The shortest range, the shortest loop of a magnetic field equals the outside diameter of the superconductor. Then I looked at a resistor, and currents flowing through a resistor. You get a positive voltage on one end and negative on the other, and this difference allows the electrical field to leak out from the positive to negative around the resistor. On the superconductor, there is no resistance. No electrical field leaks out. The electrical field is entirely confined within the superconductor, and so the superconductor dramatically affects the range and the strength of the electromagnetic field. Then I wondered, does gravity participate in such a relationship? Does a strong nuclear force, can it be affected by a superconductor? And I went down to see Puthoff in 1992 and talked to him about this. And he was working with something at that time that was called the Goldstone boson. It's very similar logic. But what we found is that the gravitational and nuclear forces are not adjoined in this superconductive relationship. And I wondered, why not? What's missing? What could be done to the superconductor to get all the natural forces to participate in this reaction?
Interesting. Now, you also went to Anaheim in 1995 to view James Patterson's cold fusion cell. Can you tell us more about what happened there?
I went to the PowerGen conference in 1995 to witness James Patterson's and his clean energy technology company's cold fusion cell. And there I saw that he used a preheater to get the reaction going. I wondered, what could thermal vibrations have to do with a nuclear reaction? Thermal vibrations only have energy levels of a fraction of electron volt. How can these low-grade thermal vibrations influence nuclear reactions? Nuclear reactions have energy levels at tens of thousands of electron volts, even millions of electron volts. So what did this process of thermal vibration have to do with James Patterson's process? Then I found out that a proton conductor, that's what he was using, where he dissolves protons, deuterium protons, into a palladium structure, can sometimes be superconductive. Then I thought, is vibration the process that adjoins the strong nuclear force into the superconductive relationship? And I found something else out when I was there, that the size of the structures, the micrograin structures that Patterson and for that matter many other cold fusion experimenters were using, is about 50 nanometers. So then I multiplied the thermal frequency, 10 to the 14 hertz, times the diameter of the palladium structure, which was 50 nanometers, and I got a velocity of 1 million meters per second. And I wondered, what is that? Is that the velocity of sound in the structure? Is it the velocity of light? What meaning does that 1 million meters per second have?